Hey there, awesome physics students. Let's talk about torques and forces in the body. In particular, I want to do an example problem where we examine the forces on the forearm. In particular, we're going to have the weight of the forearm down, and we're going to put that at the center of mass of the forearm, and we're going to assume that is about in the middle of the forearm. So for my forearm, I'm going to estimate that to be about 30 centimeters long, and so then I'm going to estimate the center of mass to be roughly in the center. It's not exactly, but it's a pretty good estimate. And that's going to point down directly at the center of mass there. So that's going to be about 15 centimeters from the end of my arm. And then I'm going to, the forces up, or the other forces that may act on my forearm, clearly there's going to be a biceps force acting on my forearm. That's going to pull, my biceps are pulling my forearm up. And we want to know how much force do I need to keep my from the biceps to keep my forearm level. So let's go ahead and do the first step of any of these problems, which is to draw a free body diagram for the object of interest. In this case, this is my forearm. So to be clear, I'm going to treat my forearm, just this lower arm part, as separate from the rest of my body. Right? So as I said, I have the forces on this are going to be the gravitational force that's going to act at the center of mass. So that's going to be about 15 centimeters from the end of my arm. And then I'm going to have the biceps force. Now I can look at my biceps, and if I estimate my joint, if I place my joint at the very end of the forearm, it's not exactly there, but that's good enough for this particular problem. Then I can estimate my biceps to be connected to my forearm about 2 centimeters from the joint. And so my biceps are going to pull up like that, and that's going to be the force of my biceps. And like I said, that's going to be about 2 centimeters from my from the end. And now let's think, are these the only forces acting on the forearm? Well, if this were true, if these were the only forces, I think you can see they're going to tend to rotate this forearm clockwise. Meaning if I place my axis of rotation here at the biceps, this is going to cause a clockwise torque about where the biceps connect. And if I place the axis here, this is also going to cause a clockwise torque around the center of mass of my arm. So there must be another force acting on my arm. And in fact, that's where my joint is connected. This is where my upper arm is connected to my lower arm. There's a joint there, and there's going to be a force from that joint. And that force has to point down. And how do I know that that joint force points down? Well, I need a counterclockwise torque. If I put my axis of rotation at the biceps, I need a counterclockwise torque, and so that means that my joint force has to be down. All right, so let's go ahead and work this problem. Let's imagine that the mass of my arm is about 3 kilograms, so that's about 6 pounds. That's not that's a realistic estimate. And what we want to do is we want to find the biceps force here. Okay, so how are we going to do this? Let's place our axis of rotation at the end here. And so we want to locate our axis of rotation, and then we want to establish a coordinate system, positive for rotation. So we're going to say positive rotation is counterclockwise is positive, and then we want to use a standard XY coordinate system like this. Okay? So now what do we do? Well, I think now that we've got the free body diagram drawn, the axis of rotation labeled, the positive coordinate systems established, now we can start summing forces and torques. So we do the same thing we did before. We're going to say that because the acceleration is 0, the sum of the forces is going to be 0. Now there's only forces in the y direction here, so we only have to sum the forces in the y direction. That's going to be 0. And we're also going to use the fact that the sum of the torques about any axis is going to be 0. Okay, so let's begin with these. Let's go ahead and begin with the sum of the forces. And so if we sum the forces in the y direction, this gives us, well, I have the biceps force is unknown, and that's up, it's positive. The joint force is down, that's going to be negative, so that's a negative joint force. And then we have the gravitational force of the weight of the arm. We know the mass, so we actually know this force, and that's down as well. So that's negative. Okay, and keep in mind, I don't need to worry about any of the distances for this computation because it's just forces. Okay, so I set that equal to 0 because there's no acceleration. And I notice that I have two unknowns here, but I only have one equation. I cannot solve this. I need another equation. So let me sum the torques. Now I just have to choose what axis I want to use. A natural point is the joint force. It's a very good idea when you're solving these problems to put the axis of rotation, when you're summing your torques, at a location where you don't know the force and you don't care. So there's a joint force here that we don't know and we don't care. That's not part of the question of what we're trying to answer on this step. So if I put the axis there, the distance to that force will be 0 and it won't come into my torque equations. So let's put it there. So if my axis is there, then I'm going to have a counterclockwise torque for this biceps force. And so if you're not sure how to see that, put your axis here and then think, is this going to cause it to rotate counterclockwise or clockwise? I think clearly you can see it's going to cause it to rotate counterclockwise around my axis point. Okay, so that's going to be FB times the distance there. My R vector points from the axis to where the force acts, and that's 2 centimeters. I'm going to put the number in here. Now you might think, do I have to convert centimeters to meters? Well, let's see. I'm going to leave it as centimeters for right now, and then if we need to, we can convert it, but let's just leave it for right now. So there's my R vector, and then you notice that the force and the R vector are perpendicular to each other, and so I'm going to have a sine of 90-degree factor here. Sine of 90 is 1, so I'm just going to leave that off. And that I decided was counterclockwise, which is positive, so this is a positive torque. Okay, so that force is done. Of course, there's the joint force, which is going to be 0 because the force and the axis are at the same location. So my R vector will be 0, so there's no torque from that one. And then finally, I'm going to have the force from the weight of the arm itself. And so my axis is here. My R vector points like that. And so that's going to be, let's do the force. That's mg times the distance there is 15 centimeters. And then the R vector is perpendicular again to the force. Oops, it points down. And so there's going to be a sine of 90 in there. Sine of 90 is 1, so I'm not going to write that. And then this causes, if I put this as my axis, this is going to cause clockwise rotation. And so I need to put a negative sign in here because that's opposite of my positive convention. Okay? So they're just going to have 3 forces here, so I'm going to have 3 torques. I've accounted for all of those, so I set that equal to 0. And if you look at this, here I know M is 3, and I know G is just a number. The only thing I don't know is the biceps force. So I know I have one equation, one unknown. I can solve that. That's my favorite kind to solve. So I want to solve for FB here. So what I'm going to do is move this to the other side, and then I'm going to divide both sides by 2 centimeters. So I'm doing the algebra in one step. If you need to take a second to do some algebra, please do that. So this is going to be, I'm going to put in the numbers here. So this is going to be mg, so m is 3 kilograms. G is 9.8 newtons per kilogram. There's 15 centimeters here. And then I'm dividing it by the factor here, which is 2 centimeters. And notice that I kept the centimeters, I didn't convert them. Notice that that will cancel here. The reason it cancels is because these torques sum to 0. If the torques did not sum to 0, I would not be able to cancel them like this. But they do. So I can cancel, I could have used inches. I could have used, football fields or something like that, some weird unit. I'm not going to, but I'm going to stick with centimeters for right now. Okay, so now I can just punch this into my calculator. So I have 3 times 9.8 times 15 divided by 2. And when I compute that, I get the biceps force is equal to 221 newtons. Now let's think about whether this force makes sense or whether this force surprises us or not. if I convert this into pounds, this is about 50 pounds. Not exactly, but about roughly 50 pounds. That seems like a lot, considering that the mass of my arm is 3 kilograms. 3 kilograms is about 6 pounds. But let's think about this. The distance from the axis to the biceps force is 2. The distance from the arm to the center of mass of the arm is 15. So this is a factor of about 7 to 8 times, 7.5 exactly, 7 times bigger of a distance to the force. And so we do expect this force, in order for it to produce the same torque to oppose it, this force needs to be about 7 or 8 times bigger than the weight of the arm. And so if this is about 6 pounds, 7 times 6 pounds is going to be about 42 pounds. So about 50 pounds, that's actually quite reasonable. Okay, so this also illustrates why the biceps force is so big, is because it's acting at a very short distance from the axis of rotation. And so that in order to produce a large torque, the R is not going to be big, but the F needs to be big so that the torque will be big. Here, the weight of the arm, the R is large already, even though the force is very small, and that can still produce a sizable torque just because of by virtue of the larger distance from the axis of rotation. Okay. Now, let's say we wanted to find the joint force, just to kind of give us some finality here. I could go back and I can use this equation here to find the joint force. So let's go ahead and do that. I'm going to add the joint force to both sides, move it over here, and it becomes positive. And so then I get the joint force is equal to the biceps force minus the weight. And when I plug and I know this number is 221 and this is 6 and 9.8. And when I plug those numbers in, I get about 192 newtons, which is still pretty sizable. It's not quite as big as the biceps force, but it's still pretty big. And that's necessary because I need a large force here to oppose that biceps force, so that the whole forearm doesn't accelerate up or down, right? If the joint force was small, like the weight of the arm, then the net force, the biceps force, would produce a large upward force and just holding our forearm horizontal would cause our forearm to accelerate up, and that's, of course, not going to happen in this situation. All right, so this is an idea of how to work some of these forces and torques in the body. You need to actually measure some distances. Where your tendons connect to your bone actually matters quite a bit in terms of determining the force. You can imagine that if I were to hold a weight in my hand at the very end, then that would cause my biceps force to be even larger than this. This would magnify the biceps force quite a bit, because now it has to not only oppose the weight of the arm, but this extra load here. All right, I think that's enough for this problem. Yeah, hopefully this was clear.